right, I'm giving this presentation through an SSH tunnel, so wish me luck. What I'm going to talk about today is the brain imaging data structure that has already come up a few times today, which is basically an attempt to standardize the storage of neuroscience data. So what I'm going to tell you about today is three things really. I'm going to give you a crash course in what BIDS is and what BIDS data looks like. I'm going to try and convince you that BIDS data is a useful thing, not just for doing the right thing and sharing your data, but also for working with your data. So I would argue that the best time point to convert your data to BIDS is at the start of your process before you analyze the data. And then what happens when you do that is that all of your data analysis code is now reproducible and can be shared along with your BIDS format data. Don't do what I did, which is to analyze a data set for years, then realize that I have to share it, convert it to BIDS, and then spend 2 months rewriting all the analysis code so that it actually works with the BIDS data, only to realize that you don't get the same result. Avoid that situation by converting first, and you'll gain access to some cool tools, as I'll show you in a minute. And the final part of the talk, we're going to talk about how you get your data into BIDS format. So I'm going to give you a demo of DCM to BIDS, which is a tool I've developed for taking MRI data into BIDS. So what is BIDS? Well, at the moment, the current release version of BIDS covers mostly MRI, but there is emerging support for other things like MEG data, behavioral data as it relates to neuroimaging. But there are plans to extend this. And if you go on the BIDS website, you can get involved with all of these extensions to make BIDS apply to new imaging modalities or to make BIDS apply to other stages of processing. So at the moment, BIDS provides a specification for sharing raw data, but it does not really give you a specification for derivatives, that is things like process data, things that derive from the raw data. But that's coming quite soon, I believe. And if you're interested in these extensions, you can go on the BIDS website and get involved in the discussion about how these extensions should look. This is an open community effort. There is no committee that decides these things. You're free to jump in and tell them what you think if you feel strongly about any of these things. So what is BIDS more concretely? Well, let's take a look at a minimal example data set just to get a feeling for what this looks like. So what I'm going to do here is I'm going to just play around with the data set that I downloaded using DataLad, of course. So here's a little example data sets, and here I'm just listing the directory tree. Let me blow this up a bit so you can see. So at the root we have some general files, and then we have subfolders. So here's the folder where subject 1's data is, and inside we have subfolders for anatomical images, diffusion images, functional images. And we also have some general dataset files like this dataset description file, which contains some sort of general project metadata. If we drill down a bit further inside one of those subfolders, so here I'm going to go inside the subject 1's functional folder. And if we list that content, you get a few nifty files. And you can see the basic naming conventions that are used in BIDS. So here, for instance, this is subject 1's data for the finger, foot, lips task, whatever that may be. And the underscore bold.nii means that we're working with bold contrast neuroimaging data. So this is going to be 4D nifty data with the actual raw Fmri data. Here's another nifty for another task that was collected in the same session. And down here is a file that has the same prefix but a different suffix, so it ends in events.tsv. This is a tab-separated value text file, which defines the experimental events. So the stuff that you would put into your SPM design matrix to run your first-level model. Just to make it clear that there's nothing mystical about this stuff, if we take a look at the content of that TSV file, try and zoom in on this, you can see that it's pretty straightforward. So this is a table, and here's the first trial. It took place at 24 seconds. It had a duration of 1 second, and the trial type for that trial was incorrect task. So you can see how you can take this sort of table and turn it into a design matrix in your analysis tool of choice pretty easily. So that's the way BID looks. And I guess for most of you, if you've worked with neuroimaging data before, you will have your own standards and conventions. You have ways you organize your data. Why should you go through the pain of adopting this standard instead of whatever your lab is already using? Well, the obvious reason of it is why we're all here. It's about open science and data sharing, and we've already heard that if you're going to share your data, it'll be much more useful to other people if they can understand your data. So if you're following a standard format or standard structure, your data will be used by other people, which is hopefully the point of sharing it in the first place. If you use something really idiosyncratic, it's possible that no one will ever take the time to work out what that data even was. So that's the sort of open science reason, but there are more selfish reasons to do it too. So one thing is that if you're more of a user of research methods, that is, you're trying to analyze your data, you want to write a paper and get on with life, if your data is in BIDS format, you can use some cool new analysis tools. So here's a really prominent one called Fmri Prep, which we already heard mentioned, which basically provides automated pre-processing of Fmri data. And what I'm showing you here is actually a complete command that will take the example data set I just showed you. That's the first argument here. We're pointing it to that same directory we already looked at. Pre-process it, put the outputs into the output directory, work only on the first subject, and put the temporary files in this working directory along the way, and that's it. Now, those of you who have worked with MRI data before realize that there's a bit of magic happening under the hood here, because normally if you're pre-processing an MRI data set, you have to worry quite a lot about setting certain parameters correctly. Stuff like slice timing, field map distortions. These things can be a little bit hairy to figure out, and if you're working directly with something like SPM, you will be emailing your MRI physicist a lot and trying to work out exactly how you should have set these things to get the correct result. And in the end, you may never be sure that you got it. But the point is, if your data is in BIDS, you don't even have to worry about it, because all of that metadata is stored in a standardized location. And Fmri Prep can parse that metadata and work out what the correct settings should be. So there's a little bit of pain up front in getting your data into BIDS, but once you're there, things become really easy. The other side, and this is way too small now, the other way that BIDS can be useful is if you're someone who develops research methods. So the cool thing about working with BIDS is that there's quite an effort developing software tools around BIDS. So here I'm demonstrating a tool called PyBids. So this is Python code. There is an equivalent MATLAB tool if you're not ready to let go of MATLAB yet. And what this allows you to do is to use object-oriented coding, which we heard about already, to instance what's known as a BIDS layout. So what I'm doing here is I'm pointing PyBids to this directory that we already had a look at, and I'm getting back an instance of an object, in this case a layout. And then I can query this layout instance to get information about this data set that I'm working with. So for instance, if I want to know what the subjects are, I can do this, and I get back a list of the subjects. In this case, it's only 2 of those, but you can imagine how if you're writing an analysis script, it's now pretty easy to write a little for loop that will iterate over the subjects and do that. But we can also do more sophisticated queries. Here's one that returns. So here we're using the get method of the layout, and what we're saying here is take the first subject, and this is Python, so the first element of the list is going to be index 0, right? Stay with me. Return the T1 weighted image for that subject, and the thing I want back is going to be a file path. So what happens if we run that? You get back the file path where this file happens to be stored at the moment on the machine that's running this code. And now I can just take that file path and I can plug it into NiPipe or NiBabel or whatever I want to do some further structural processing of this data. And the real payoff of adopting this practice is, first of all, you don't have to memorize the BIDS standard. The idea with BIDS is not that you're going to sit there and dig through this horrible PDF with all of the rules about underscores and hyphens and so on. That's not the idea. The idea is that you use a high-level parser like this, so you don't even have to think about exactly how BIDS says you should be storing things. You just query this thing and you get your file path and you get on with the stuff that's actually interesting. The second benefit that's more subtle when you start working with it is that your code becomes a lot more generalizable than what you might be used to. Because if you think about what I started doing here with my little structural processing, if I swap out this argument to the BIDS layout and I instance the layout with a different BIDS data set, all of the code below still runs exactly the same way. Right? So I think what happens when you adopt any standard is that you discover that your code becomes a lot more reusable than what you might have had before. Certainly my experience is that my own internal standards that I've been using have been evolving over time, and that means that whenever I go switch data sets, I end up having to rewrite a bunch of code because nothing really works the way it used to work last time I used the code. With BIDS, you're somewhat less sensitive to that, although as Michael pointed out, nothing is certain in code. So that's the sort of code side of why you might want to use BIDs. So for the rest of the talk, I'm going to talk about how you can get there. So the tool that I've been making contributions to is called DCM to BIDs. There are many other ways to convert your data to BIDs data. I suggest that you spend some time researching the tools and thinking about what's easiest for you to get started with. So what DCM to BIDs does is basically to try and provide an automated conversion from raw DICOMs from your MRI scanner to fully BIDs compliant outputs. So along the way, we're going to convert the DICOMs to NIfTI using DCM to NIX. We're going to anonymize the structurals by removing the face features, which is important for data protection. We're going to move everything into this right place, obviously, and we're going to also play around a little bit with the header information. So in the BIDs format, you may have noticed that along with every NIfTI image that you're sharing, which contains the actual Fmri data, there is a sidecar file that ends in the JSON extension. And that file is basically there as a workaround for the fact that the NIfTI header doesn't contain all the information that you'll find in a DICOM header. So when you convert your raw data from DICOM to NIfTI, you're inevitably losing a little bit of metadata along the way. And the workaround for that in BIDs is to have another file that stores all of the DICOM header metadata information in a standardized way. But unfortunately, the conversion, so DCM to NIX actually generates that sidecar file for you initially. Sorry about that. But it's not complete. So DCM to BIDs provides some tools to allow you to sort of extend that sidecar to get all the way to something that's compliant. And we'll also create these other project files that we saw earlier in the presentation. So let's convert some data. Here is an example data set that I downloaded using DataLad. This is a phantom that was scanned at Dartmouth, I believe. And this is the sort of directory tree that you'll see when your data comes off the scanner if you have a Siemens scanner. So you'll have a bunch of folders. They correspond loosely to scanner runs, but not exactly. Some scanner runs generate multiple folders. Some of the folders contain generate multiple NIfTIs. Some of them don't. It's all a bit of a mess. So now we want to get this into a BIDs format. Well, the way to achieve that in DCM to BIDs is going to be to start thinking a little about how DCM to BIDs works. So the basic idea of DCM to BIDs is that we're going to have a configuration file, which is yet another JSON file, which basically defines the mapping from raw DICOMs to particular BIDs outputs. So you, as the end user of DCM to BIDs, the thing you have to worry about is how to set up this configuration JSON file so that your data is parsed appropriately. That's the one thing you have to do as the user. Everything else gets taken care of. So to get us started with setting up that configuration file, we're just going to generate an empty configuration file and do a little test run. So don't worry too much about the code up here. All I'm doing is generating a JSON file that, if you open it up in a text viewer, looks like this. So there's a single entry in a dictionary or a struct if you come from MATLAB. And the key there, or the field name, is descriptions. And this square brackets in Python and in the JSON corresponds to an empty list. So the idea here is that every entry in this list is an output that we want to generate in PyBids, that we want to get out of this. And we're going to go through our DICOM data, and we're going to try and find, for each output, we're going to see if we can find an input. So to get us started, we're just going to run DCM to BIDs with this little dummy configuration file, which will turn out to be a useful thing. We'll see in a minute. So the basic syntax for using DCM to BIDs, this is another command line application, although you can use it as a Python library if you want to. So we're going to point it to this test directory that we already looked at. We want the outputs of that to be participant 1 in the BIDs output. And this is the configuration JSON that I just created, which is basically empty at the moment. And we want the output, the BIDs data set, should be saved in the output directory. And that's it. So if we run that, eventually we'll get an output. Yay. And if we now look at the output directory, well, I've done something kind of weird, right? So I've generated an empty configuration. I've run a bunch of code, so I haven't got much. By definition, there's nothing in the output directory, right? So what the useful thing about doing this is that when DCM to BIDs runs, it internally does a full DCM to NIfTI conversion of all of the input series. So all of the series have been converted and dumped into this temporary folder. And basically only the NIfTIs that match something in our configuration file get put into the actual bids output. Everything else gets left here. And the useful thing about that is that now to set up our configuration file so that we can actually recognize something, we can start looking at these sidecar JSON files that came out of DCM10IX. And the basic goal then of what we're trying to do here is that we want to put stuff in our configuration JSON that is diagnostic of our sequences. And the way we're going to do that is by looking at these sidecar JSONs. So if we take a look at one of these, this is for the T1 weighted image. This is the sidecar JSON, so the stuff you'd ordinarily find in a DICOM header, and you can see this data came from Dartmouth. That's not very helpful for this particular conversion, but there you go. There are various fields in here that you could use, and all of these are basically potential criteria that we could use for recognizing this file as a T1 weighted image in this case. Particularly useful one is the series description field, which in this case has been named very helpfully, right? So the series description in this JSON is an at T1 weighted. That sounds like it might be useful. So what we're going to do now is we're going to add to our configuration file something that states that for the anatomical data type with T1 weighted suffix, recognize something if in the series description you have the field this kind of string somewhere. You can do this, so here I'm using Python to generate this variable and then writing it out to JSON. You could write the JSON by hand if you're a masochist, or you could use MATLAB. It's up to you. But anyway, what I'm generating is just this JSON file in the end. So you can see that the descriptions field that I showed before now has an entry. And there's only one entry, and it is this thing that I set up before to recognize the T1 weighted image. So let's try running the code again. And now that we've added that T1 weighted field, hopefully we will get something out of the parser this time. So the code is run, and if we now take a look at the output directory again, we've got something. So you can see now the output directory has a bunch of files that are expected by bids, like the dataset description, and we have a folder for subject 1, and a NAT subfolder, and in there the T1 weighted data, all named according to the bid standard. We've also set up some of the initial project files. So for instance, the dataset description file that I mentioned before is required by bids, and it has some fields that the bids validator might want to see. And those have been initialized with mostly empty values, because these things you do have to provide yourself, but in some cases, like the bids version, we do know which version we're aiming for, and that's useful for the parser to understand your data. So now to scale this up to convert all of the series that we collected, I could bore you to tears and show you all of the criteria and all the considerations, but I'm not going to do that. I've cooked one up already. And just to give you an idea of what that looks like for this example data set, here's the full configuration file. So the descriptions list is now longer. We have the anatomical that we already saw. Here's the functional series, which we recognize by looking for the pulse sequence details field being bold. Here we're setting the task name, which is an important custom property that you don't get out of DCM10IX. You have to set this. And then we have various parsing of the field maps, and this part can be a little bit hairy, to be honest. So this example is available in the project repository if you're interested in doing some field map conversions. It's probably the hardest thing I've worked with in terms of bids conversions. So take a look at that in your own time if you're interested. So now we have the complete specification, right, for how to convert this. Let's see if we can actually get a conversion this time. So we're running one final time, now with the complete configuration file. And this time, we've got something that looks more complete. So for subject 1, we now have an ANAT folder, as before. We also have an FMAP folder, which is where the field maps are stored. You can see we have 2 magnitude images, we have a phase difference image. In the functional folder, we have 1 run of functional data. And that's it. So that looks like a BIDS data set. But the question that arises at this point is, how can we be sure of that? Instead of trying to just submit this somewhere and having someone complain later, we can check for ourselves using this cool tool that other people have developed called the BIDS Validator. Now you can go to the BIDS Validator website and just plug in your directory folder. It won't actually upload anything, it will just run it. But you can also run it on the command line if you're more technical. So we have this available on the imaging system here at CBU if you're interested in that. So if we plug our output directory that we just generated into the BIDS Validator, we get this nice message that it's BIDS compatible. Fantastic. This basically never happens with real data. You always have some problems. But but I've cooked this example to be perfect. And then you get a little summary of what the data is like, what the tasks are like, what sort of modalities you have. And this is a really nice way to sort of target your conversions, right? So when you start converting, you're not going to get perfect, but the BIDS validator actually contains really helpful feedback on exactly why, in what ways you're falling short at the moment. And that can be a really useful way to quickly get your data all the way there, sort of. So just to wrap up, here are some useful resources that you can look at. This slideshow is available online, so you can check these out in your own time. I especially want to mention Michael Notter's SniPipe tutorial, which is a really good way to get started if you want to really do a deep dive into Python and neuroimaging and working with BIDS data there. There's some cool stuff there. If you want to look at this code, you can check out DCM to BIDS on my GitHub. And I guess the final thing I just want to mention is that this entire presentation is a Jupyter notebook. It looks like this in its more standard presentation. So if you're interested, you can run this yourself. You can either attempt to download it by going to my GitHub here and figure out if you have all the requirements. It should just work on the imaging system here at CBU. Or you can press this little button and it will fire up this thing called Binder, which is basically a cloud-based way to run a Jupyter notebook. So you don't even need to install anything to try this out, and all the data should download and everything should just work. That's all I have for today, I think. Thank you.